So we want to thank everyone for coming today to the Center for Connected Multimodal Mobility's Distinguished Speaker Series. I'm going to introduce Dr. Ronnie Chaudhry is the director of our center, and he is going to introduce our speaker today.
Thank you, Charlotte. So we are glad to have among us Dr. Patire. So I'll just mention short bio of Dr. Patire. Having earned master's and bachelor's degrees in electrical engineering and computer science from MIT, Dr. Patire brings 2 years of experience in satellite telecommunication systems engineering and 3 years of experience in embedded systems hardware design. While building an on-chip bus architecture to handle the logistical problem of moving bits between multiple consumers and producers of data, he became interested in pursuing analogous problems, moving people from origins to destinations in a physical world. Dr. Patire completed his PhD in civil and environmental engineering at UC Berkeley, focusing on traffic flow theory and bottlenecks. For the past several years, he has helped to bring a number of path projects to completion, including Mobile Century, Mobile Millennium, and the Hybrid Traffic Data Collection Roadmap. Along the way, he has been a team leader on large-scale problems that involve GPS-based probe data, data assimilation, and flow models in the context of integrated corridor management. In his present position, Dr. Patire is responsible for the analysis, modeling, and simulation of the I-210 corridor as a part of the Connected Corridors program. In addition, he pursues research interests involving data analytics and machine learning. So it's my pleasure as the director of C2M2 to introduce Dr. Patire. So we are all very excited to hear from you, Dr. Patire.
Thank you so much for the kind introduction, and thank you so much for giving me the opportunity to present this work. So, as promised, I'm going to provide a peek under the hood of the Connected Corridors ICM I-210 pilot. So, greetings from the Institute of Transportation Studies at UC Berkeley. I should say a few words of introduction. The Institute has a number of research centers, and I'm affiliated with PATH. Within PATH, there are a number of program areas, and today I'm going to tell you about Connected Corridors. The Connected Corridors is a collaborative program to research, develop, and test an integrated corridor management ICM approach to managing transportation corridors in California. ICM seeks to address the total system holistically, and this system consists of people, organizations, hardware, and software. So we focus on both the software human aspects as well as the technological aspects of corridor management. I need to emphasize today that I'm not just presenting my own work, but I'm also presenting work with my colleagues and friends, and I feel fortunate that I have the opportunity to work with such a dedicated team. Over the years, Connected Corridors has benefited from the efforts of a diverse group, including students at all levels, undergraduates, master's and PhD students, as well as postdocs, researchers, professors, staff, visiting scholars, and even professional managers. And I've attempted to list them here. Finally, I would like to acknowledge our partners without whom Connected Corridors would not be possible. We benefit from steadfast support of Caltrans and LA Metro, as well as all of the participating cities and agencies. So I have a two-part agenda. In part one, I'm going to provide an overview of the Connected Corridors program. I'm going to talk a little bit about the objectives, the system architecture, and operation. Then part two, I'm going to try to focus on some key components under the hood. And so the key things that I hope I have time to touch on are data quality, estimation of traffic conditions. Specifically, I'm going to talk a little bit just about arterial estimation. And then we're going to talk about model-based prediction of traffic management interventions. And then finally, a little bit about predicted benefits. If I run out of time, maybe I won't hit all of these, but this is what I'm going to try to talk about today. Okay. So first, let's have an overview. This is a satellite image of the LA basin. Now, unfortunately, we're not yet sophisticated enough to manage all of this traffic. So we're focusing just on the network shown in blue. So if I zoom in, our corridor extends about 16 miles east and west, and about 4 miles north and south. It includes the cities of Pasadena, Arcadia, Monrovia, and Duarte. And the supporting arterials, drawn in the thick colors, are in play as arterials to help support freeway operations. So, a few key objectives. Of course, we need to bring together our corridor stakeholders to create an environment for mutual cooperation and collaboration. We're developing and piloting an advanced ICM IT system for use by Caltrans and local stakeholders to manage their corridor. And our sincere hope is that this is something that will be replicable, and that what we're building is useful enough that it can be fanned out across other corridors. We hope to demonstrate project effectiveness that will lead to more opportunities to try out more advanced tools and more capabilities. And the last bullet I put in a different color, because really I'm going to be focusing here on increasing capacity on arterial reroutes during freeway incidents. Okay, so our initial focus is not dealing with recurrent traffic, but only freeway incidents, and modifying signal plans, rent metering plans, and route messaging on the fly. So you always need a good motivation slide. So in this traffic accident in 2014, one big rig ended up in the Gold Line transit tracks that run in the median of the freeway on our corridor. This incident is now memorialized in Google Earth as a bad day for commuters and a glorious day for traffic researchers who can now obtain a direct measurement of freeway jam density. Sensationally disruptive events happen from year to year on the I-210 corridor. For example, a big rig ends up blocking the Gold Line rail about once every 2 years. The picture in the upper right shows a complete freeway shutdown resulting from a suspicious package that was discarded from the transit terminal and landed on the HOV lane. They had to send out a robot to go check it out and make sure that it wasn't a bomb. So this slide is a cartoon depicting some ideas of how one might manage an incident. And the concept is to adjust traffic signal plans and to provide extra capacity on a parallel arterial or two to help to address some of the demand that cannot be served by the freeway when it's blocked. And so, as you can imagine, this is a great example of the cyber physical system. You have people, you have infrastructure, you have the technology that's trying to help make some good decisions to manage the system more effectively. So for the response plans that we're considering in this corridor, they can involve a number of different elements. It can include the reroute itself, information dissemination via changeable message signs or trailblazer signs along the routes. intersection signal control request, adjusting the cycle duration and offset the signal to provide additional green time to preferred movement, and also rent meter control requests to prioritize vehicles entering the freeway at the end of a reroute. So in this slide, I'm showing 3 possible responses to an incident that might be located somewhere in the blue region of the freeway. And so you can imagine you would want your response to be commensurate with the impact to the system. So in the top, for a relatively short freeway queue, maybe you would have a short reroute. And for maybe a medium length queue, you would have a medium length reroute. And if you expect a bigger disruption, maybe you would have 2 reroutes. Or maybe if this is an incident happening 2 a.m. on a weekend, no fatalities, no chemical spill, nothing crazy, well, lucky day. Maybe there's no need for a detour. It's just the management agency should do what it normally does and send out a team to clear the incident. Okay, so I'm going to talk a little bit about the system architecture that we're building to help manage this cyber-physical system. Okay, so this slide shows one view of the system. The green boxes represent software systems that provide data and also control infrastructure assets such as signals and rent meters. The suspenders person, or the suspenders people here, represent a corridor manager or a traffic operator, or one of the humans in the loop. I should say something about these green boxes. So on the upper left, for example, KITS is the software system used by LA County to control their signals. And Transparity is the product that Pasadena uses. And our system has to be able to interact with these other systems. The green box, this ATMS box, is the interface for Caltrans, where they enter in a freeway incident and approve or disapprove plans. And the purple box is the interface for cities, where they can see a global view of what's happening, say, outside of just their own city, and again, to approve or disapprove response plans. Now, the red and blue boxes were developed by our Connected Corridors team. And it's our hope that this will be leveraged by others in the future. The Connected Corridors ICM system is a fully automated cloud-native solution. And what that means is there's no data center, no hardware to procure and maintain. It's push-button deployment, and you pay for what you actually use. And the system is designed to deploy anywhere. It's not specific to any district or location. And the system is scalable to adjust to corridor size and modular to adapt to local needs. And that's part of the power of using cloud technology. So this talk is going to focus on the decision support system, which, as I've alluded to earlier, is what we use to help decide among some possible interventions that one might want to deploy to manage incident congestion. Okay. So inside the DSS, there are 3 main blocks that I want to talk about. So there's a response plan generator that contains an inventory of response plan elements and rules for allowable combinations of these elements. And it selects plans for evaluation deployment. There's a prediction blocks, and prediction inside contains an AIMSA microsimulation model of the corridor. And its job is to predict future effects of interventions and to evaluate potential response plans. The estimator provides situational awareness, and its job is to provide freeway queue status to the response plan generator, and then to provide an initial traffic state for the prediction engine. And so I'm going to talk about various parts of these boxes. This slide illustrates the incident and the response plan life cycle. There are 4 main parts. In phase 1, an incident's reported, and a response plan is implemented. In phase 2, there might be some adjustments that are made. And at some point, that incident on the freeway is cleared. Now, when it's cleared, that doesn't mean that you're done, because usually at about this point, vehicles have rerouted themselves, and there's a lot of excess vehicle accumulation on city streets. And so there might be some phase 3 where the response plan continues and stays around long enough to help get people back on the freeway. And then finally, in phase 4, the response plan is terminated and things go back to time of day. There's one important point I want to make about this that we learned by simulating incidents over and over again. And that is, when you consider the system as a whole, it's important to greenball the downstream ramp meters to allow maximum inflow of vehicles. And that isn't what you would come up with just by looking at the freeway in isolation. In a recurrent situation, these ramp meters have a purpose, but during an incident, we need to provide some extra priority to the arterial streets, and to reduce that congestion, and that makes the whole system work better. Okay, so now I'm going to give a small example of the operation of this system. So in this slide, I've reorganized the boxes that I've shown you before to try to emphasize with the green arrows the communication that takes place. So we imagine a freeway incident being entered into the Caltrans ATMS and then being communicated to the response plan generator. So the decision-making process looks like this. Plans are pre-scored based on traffic engineering judgment, the results of simulation studies, and stakeholder preferences. In addition, the rules take into consideration the incident attributes, for example, the location, the time of day, the number of lanes blocked, the historical demand and the queue forecast, asset availability, for example, can I even control that signalized intersection, or is communication down? Estimation results for the queue length and initial state, and the prediction scorecard. And I'll explain about some of these things later. If there's a data outage, then estimation and prediction become impossible, and all that you can do is rely on your pre-scored plans. If there's some kind of communications outage, it could be that you have no assets to control, and you can't even deploy a response plan. Okay. This slide is an overview, and I'm going to return to this later. But just notice the green arrows. Estimation is always running and providing situational awareness. And the top N plans are evaluated by the prediction system, and the results are returned to the response plan generator. Now, that number N is determined by how many AIMSUN licenses you have and how much money you want to pay Amazon for the compute resources for however many simulations you would like to run. Okay, at the end, plans are ranked based on their scorecards, and the top ranked plan is sent out for approval. If that one's disapproved, then it'll send out plan number 2. That's the system in a nutshell. Okay, so that concludes part 1 of my talk. And so hopefully we'll have enough time to get through my 4 subject areas that I want to share. So the first one is data quality. And I'm just going to show some examples on the freeway. So the importance of high quality data cannot be overstated because it's the very lifeblood of traffic analysis and management. I was so naive when I started this project. I really thought that you could just get your sensors working You could look at the data, correct any configuration data or anything that was wrong, and then move forward. But that's really a fantasy. Data quality needs to be a continuous process, and generally you can't fix everything at once, and there's no notion of done. I'm going to give you an example timeline of events. In 2016, we did an initial check of configuration data, and we fixed things. In 2018, there was something called an IP conversion, which involved installing new physical devices, new controllers, and new physical connections. So they updated their communications from old Viterbi modems over twisted pair to a fiber based IP system. And then in 2019, the configuration data needed to be checked and fixed again. I'm going to give you an example of just some of the things that we found. So this slide shows flow rates from loops throughout the day. And the red, green, and blue time series are from consecutive detectors along the freeway, eastbound on the left and westbound on the right. And clearly, the green pattern on the left matches the red and blue pattern on the right. And this is just an example of a detector that was, or a set of detectors assigned to the wrong side of the freeway. Another example that is actually quite common is the swapping of the H of V detector, I'm talking about loop detectors here, with that of the leftmost mainline detector. The mainline detector tends to have much higher flows. Now on the left, you can see a consistent and unrealistic flow difference across successive detectors. So these are, the green and the blue lines are closely spaced or consecutive detectors along the H of V lane. And on the right, you can see that this has been fixed and that you get much more consistent flows. So one of the things that I did with some students was to create some automated tools. And it's lucky that we did this. This slide shows 4 screenshots of a dashboard. It downloads data once per day and searches for a set of suspicious features and then categorizes each sensor based on one of 4 colors. So for example, green means okay. Yellow means the data was present, but we didn't have a specific check for that data. When it goes dark, that means we've lost at least 40% of the data on that day. Then orange means that it's suspicious. And so during the IP conversion, what would happen is that these green sensors would go dark, and then sometime later, they would light up in orange. And at first I doubted our own dashboard. I'm like, really, this can't possibly be right. We fixed the configuration data, but why should this change the configuration? They're just updating the communications. But when we examined the data, it turned out that the configuration needed to be fixed again. And so there's some lessons learned about data. I've seen graduate students waste a great deal of time taking the data as given, and sort of it doesn't quite work out with the math. And I think it's really crucial to think critically about the data in addition to thinking rigorously. You can't just take the data as a given. In a live system, sensors can come and go underneath your feet. Don't underestimate the utility of automated tools and dashboards to check configuration, information, and data quality. And in an increasingly data-driven world, methods for handling missing and erroneous data will only become more important. One thing that we've worked on, which is really fun, is looking at some of the patterns that we found in HOV data and different types of data, and trying to apply that more broadly. Okay. In this next part, I want to attribute this work to Kijun Gan. This work is an important part of connected corridors because it fulfills a critical function. If there's any really detailed questions, I'll have to refer you to the report, but I just want to provide an overview of how we're estimating arterial traffic. Okay. So the question is this: how do we generate an initial traffic state from which to kick off a simulation. Now, we have some available data. We have an initial state from a calibrated model for each hour of the day. We also have field observations from loop detectors where available, and they're available along the main arterials. Now, the challenge here is that there's no such thing as an average day. So on any particular day, there's going to be something a little bit different about it than what your calibrated model has as an initial state. Now, it's sometimes typical to use a warm-up period for these sorts of models, but that's time-consuming in a large network. And there's a little bit of a controllability problem because it's not clear that it's easy to just push your system towards the initial state that you're trying to achieve. Our approach is to use field observations to estimate the number of vehicles at each intersection approach and then insert vehicles into the initial state at the start of the prediction simulation. So just as an overview, as shown on the left, at the major intersections, we have some combination of left turn, advance, and stop bar detectors. And the goal is to estimate the number of vehicles in each of 3 queues, those going left, those going through, and those turning right. This slide shows flows versus occupancies from an advanced detector on the left and a stop bar detector on the right. And the color code corresponds to different times of day. And there are some interesting correlations here. The key is to calculate occupancy thresholds shown in these vertical blue and red lines for each intersection approach. And these thresholds can be explicitly calculated based on the road geometry, sensor placement, signal settings, and an assumed saturation flow. Three regimes can be identified. This regime 1, which is this uncongested regime. Regime 2, which is congestion but with no downstream spillback. And then this regime 3, which is congestion with spillback. This threshold calculation was validated in simulation. I'm going to show on the left is the setup, where there's an intersection, and at the very bottom there's a bottleneck that's been prepared to limit flow. And then on the right, we have the flow versus occupancy plots. Demand is gradually increased to create congestion, and the calculated thresholds in blue and red agree with the breakpoints that are measured in the flow versus occupancy plots. And it also looks similar to what the measurements we have in the field. Okay, it was necessary to validate the Q estimates in real life, and it turns out that there's a linear relationship between travel time and total Q along an arterial in the congested regime. The picture at the bottom shows the test site on our corridor where both Bluetooth travel time and loop data were available for comparison, and lucky, in the afternoon peaks and in the morning peaks, it's in congestion, so we were able to test this out. On the left, this slide shows the Bluetooth travel times in blue and the Q estimates based on the method in the other colors. These time series match qualitatively during the congested period shown in the red dashed rectangles. On the right, this slide shows the travel time plotted against the total Q estimates generated by the algorithm. The relationship appears linear, as expected, and so that's pretty good. This slide shows a part of the Aimson network in the lower left, and on the upper right, the slide shows a zoomed-in portion of the network in which vehicles generated from field detector measurements are inserted into the initial state. Now, there's one last piece of information that you're probably wondering about. If we insert vehicles into a microsimulation, how do we give them destinations, right? That's really important. So what we did is this. From simulation of the calibrated model, we obtain a destination distribution for each time period and day type at each intersection approach. Now, this has limitations, and we're working to improve it, but it gives us a starting point. So given that destination distribution and the sensor data, we determine the number of vehicles in each queue at each intersection approach. We assign an appropriate destination based on that distribution. And then we assign the vehicles from downstream to upstream. And when a dedicated lane is full, say for a left turn, then vehicles are assigned to adjacent lanes. Okay. So this is my second topic. Or actually I think my third. I'm gonna talk a little bit about prediction. Okay, so first let's just take a step back and talk about modeling. So what's the purpose of a model? Well, at the beginning of this Connected Corridors project, we needed to understand how to manage incidents on the I-210 corridor. We needed to take into account the short-term traveler responses, such as en route diversion, triggered by unusual congestion or information dissemination. We use the model to help guide assembly and selection of appropriate response plans, try out some different control parameters for the signal plans, and see if these things work. It was really important to be able to use the model to communicate with stakeholders about what they thought was going to work or what wasn't going to work, and if they believe that we're understanding the problems on the corridor. Okay, so what's the purpose of the model in real time? We're trying to do some kind of model predictive control where we're able to forecast the possible evolution of the incident under different control scenarios, to facilitate computation of a performance scorecard. And I'm going to talk more about the scorecard later. And then we need to provide enough fidelity to decide among available options. The prediction does not have to be perfect. We're never going to get it to be perfect. It just has to be good enough to be able to distinguish between a menu of possible options. And at the end of this, we're just going to calculate a delta between choice A or choice B, or this kind of thing. Okay. I want to talk a little bit about this model. This is one of the largest microsimulation models in the world. The model has over 450 signalized intersections, 45 freeway rent meters, and 1,000 lane miles of roadway modeled in loving detail. The model extends beyond the main corridor that's being managed, because we needed to accurately capture some bottlenecks outside of that area. And we also needed to model some key arterials outside of the main area of interest to capture routing behavior that may affect corridor operations. We model some complicated intersections in great detail. We programmed in all of the signal timing plans for 24/7 operation. One of the things that pushed us toward microsimulation was the operation of the corridor. 98% of these intersections are actuated, and these actuations impact the minimum green and the extension of the green phase. And so we really wanted to make sure that we were able to model that. This is actually a really interesting discussion. Why choose microsimulation over flow-based or meso model or other types of models out there? And for the controls that were within our toolbox, the intersection and signal rent meter changes are the key components of the response plans, and that's how we're able to provide additional capacity for needed movements. And the intersection signal behavior depends on these vehicle actuations, and the microsimulation directly models these actuations. Changes in routing behavior resulting from the incident and from the response plan are key factors in the predicted outcome. And okay, you have to calibrate an OD matrix, which is a lot of work, but having this OD-based model helps you to evaluate these routing impacts. Okay, so I want to get under the hood a little bit and give you a little show and tell of the analysis that the DSS performs behind the scenes. So we're going to talk a little bit about what's happening in some of these green areas between the response plan generator and the prediction. So here's an incident that we can imagine where 3 right lanes are blocked on the westbound direction of the corridor. There are a number of routes that are possible for this incident, but I want to keep to a simple example. This slide shows the normal signal operations at the top and alternative signal operations at the bottom. The star is the location of the incident, and it also shows the rent meter rate in effect at 2 p.m. The yellow circles indicate signalized intersections where we would potentially change the signal plan depending upon which response plan we're going with. So in this example, we have to decide among 3 possible plans. Plan A, B, and C. A being you just keep the time of day. Plan B, where we would have a moderate response where we would extend the cycle duration to 120 seconds to provide additional capacity for rerouted traffic. And a plan C, where we have a more aggressive plan, 135 second cycle duration to allow even more vehicles to reroute. So how do you decide what's best? We had a lot of discussion about just what to measure and how to make a good decision. So one metric involves flows and screen lines. We look at the upstream off-ramps and the downstream on-ramps. We also divide the corridor vertically with a screen line, and we want to see if we get more vehicles across the screen line, then maybe we're doing something good. In addition, we consider area statistics. If you look at the entire corridor, the entire model all at once, operational changes in one specific location tend to get washed out. And so we divided the corridor into zones. In addition, we look at the statistics on specific routes and detours. So we look at the freeway segment from the corridor end to the incident and the detour under consideration. Finally, we also keep track of the average and the max queue. We decide what's a queue and what's not a queue by choosing a 15-mile-an-hour threshold. Now, please don't try to read the details of this slide, but what I'm trying to indicate is that all of these measures are collected into a scorecard. So we take the difference between the current operation of the corridor projected into the future and the alternative operation of the corridor, again, projected in the future. And those deltas become a subscore for each metric. And then finally, we have weights for all of these subscores, and we combine it into a single number that can be compared. And we wanted this to be parametrizable, changeable, so that we could have the conversation with stakeholders and decide, hey, which metrics are more important than others for making this decision, because it's not immediately obvious. So in this example, let's say for the 120-second cycle plan, you get a score of 82. For the 135 cycle plan, you get a score of 105. And then the response plan generator would rank these plans appropriately and make the recommendation for the 135 cycle response plan. Okay. So hopefully we're doing pretty well on time. I think this is my last topic that I wanted to discuss, and these are predicted benefits. I want to attribute this work to Francois Dion, who's performed thousands of simulations on this corridor. So, at a number of times, we've looked at the frequency of incidents on this corridor, and you've seen some sensational examples. For this study, we looked at the frequency of incidents over one direction of the freeway over 6 months, and the results were extrapolated over 1 year and for both directions. And so this resulted in 548 potential activations of the system per year. And this goes to show that our corridor is truly action-packed. Based on this, 1 hour incidents were simulated up and down the freeway, and a selection of results are shown in this table. So you can see that it was simulated over different directions, different locations, with a different number of lanes blocked. And for simplicity, I'm only going to talk about the freeway operations and the benefits to freeway operations here. The response plans almost always improved operations with higher VMT and lower VHT, meaning better movement on the freeway. This slide shows VMT impacts on the left and VHT impacts on the right for 22 simulated incidents. And so then we could take from this distribution sort of a low end and a high end and produce some estimates in dollars and cents of what the benefit might be to freeway operations. So from the distribution of results, and again, looking at the low end, the yearly benefits look to be around $3 million a year. And so this is by using a value of time for VHT for autos and trucks. This does not include potential savings resulting from fuel or reliability or for vehicles using more efficient detours. This is just a straight up, VHT calculation. On the high end, the yearly benefits look more like $5 million per year. And I always like to end on a positive note. And so I'll end my presentation here. And I would love to hear your questions and comments.
So the audience, you can ask questions or you can write questions in the chat box. So we'll be reading the questions from the chat box, and we'll, Dr. Patire will request him to respond to your questions. Yeah, you can write on the chat box so if you feel that easier. Thank you so much, Dr. Patire. It was an exciting, very informational presentation. So I really enjoyed it. So I think the audience too.
Thank you so much. It's been a pleasure.
Very practical, also very thorough research. Yeah.
Thank you so much. We really do hope to put this stuff into practice, and we're looking forward to deploying a system next year.
Thank you. Yeah, so audience, please start asking questions. But I have a question. You talked about simulation. So what type of simulation tool did you use for the research?
That's a great question.
Microscopic. Yeah.
Right. So for this project, we used AIMSUN for our microsimulation.
Okay.
Thank you.
I
think we have a question. Charlotte, do you want to read?
Sure. So the first question that we have in the chat box, it's from Wayman Jin, and he asked, what is the time horizon for real-time prediction in the DSS?
That's a great question. So right now, our time horizon is over 1 hour. That's something that we can change, but that's the time horizon we're looking at right now.
Okay, and we have another question from Peggy Wang, and she asks, what is the difference between CMS and DMS?
Okay, thank you. So I think the difference is really just cultural within our group. So when we talk with Caltrans folks, we say CMS is a changeable message sign, and we think of that as being on the freeway. DMS, it's dynamic message sign. Yes, it's the same thing, but culturally within our group, we use it to refer to the trailblazer signs on the arterials. So thank you for the question. That's only within our own group.
Okay, and Matt, you asked about getting a copy of the presentation. We will be posting the video from this on our YouTube channel and our website, and those addresses are, if you scroll up in the chat, you can find both of those addresses to find those.
So I would ask this question related to this question. So Dr. Patire, so is it okay to share your slides with the audience?
Yes, I think I can do that. Thank you.
Yeah, so if you want a copy of the slides, you can email Dr. Patire or you can contact me and I can facilitate that for you.
Thank you, Charlotte.
So what is now the status of the project? So are you going to continue for another year or it's almost done?
Right, so the plan is to deploy what we have available in May, and to fix things and to help start evaluating the benefits of this next year. Right. So we're really excited about that, and a lot of this work is so close to completion. A lot of this stuff has been tested locally on our own computers, local machines. And at this point, we've now got a lot of it running up in the cloud, and we're really happy about that.
So I have a quick question of the cloud, the delay. So what is the delay that you're finding? Because the cloud is processing the information, so the upload time, download time. So
I see.
Yeah.
So basically, everything will be running in the cloud. So if you recall the picture where I had the green boxes and the red boxes and the blue boxes, so they're all communicating over ActiveMQ, these message channels, and the red box, the blue box, the purple box, and parts of those other boxes are running in the cloud. Okay. That includes the models. That includes, NoSQL databases like, Cassandra and Mongo. That includes, there's something called the so-called this Netflix conductor. And if that sounds familiar, yes, it's the same conductor that's used to feed you, to allow you to watch a movie, right? That manages the workflows among these, these different pieces of software. So delay, I think, there's a lot of, I don't know how I can address that directly, but it's at the speed of the internet. Right. Maybe if there's a more a specific issue, I think in terms of delay, one thing that we are concerned about that we haven't yet had the time to really optimize yet is how long does it take for the simulation to run, right? And I think partially that depends on how much money you have, what kind of compute processing you want to pay Amazon. Okay. It also depends on how long do you want that time horizon to be? That was a very big question earlier. Right. Do you need an hour simulation? Do you do a 45-minute simulation? Not in real time, but compressed simulated time. What should that time horizon be, and how can you make adjustments in either your software or how you're doing things to sort of meet your time budget.
Okay. So one thing we are doing now, we are running Sumo simulation, but we are running it outside the cloud, and then we are interacting with the cloud. So we are doing cloud in the loop simulation. So that kind of gives also realistic results. So, yeah.
Right.
We can share some for results for that. And we are using the Amazon Web Services too.
Right. So I would love to hear about some of your experiences, using Sumo, and I guess it sounds like some of your work is local and some of it's in the cloud, and that's interesting stuff.
Right. So that's the one thing we are doing, the cloud edge collaboration. So we are doing the edge computing and the cloud computing. So they are working together. So yeah, that's pretty interesting. Some of the things we are doing at the edge and some in the cloud. And we're also doing doing a real world test, how much time it takes to download, upload, and run the application in DynamoDB.
Okay, great.
I think we have some more questions. Yeah.
I have a question. So sorry, this is Wayne Sirasua. I am doing research right now. I am in the field, and so I missed most of the presentation, but I am curious.
And he's from Berkeley too. Dr. Patire,
my undergrad was at Berkeley. Years ago, before you. But anyway, by the way, my daughter just got into MIT, so I'm really excited for that. But that's not my question. So, 210 Southern California, right? By San Diego?
So Pasadena, Monrovia.
Oh, it's Pasadena Freeway. So why south? Is that because of UCLA?
No. So we spent more than a year researching different corridors in California, and working with our partners to find a corridor that is, congested, and that it would benefit from this kind of project.
Pasadena is definitely congestion.
Right, and then another part of the puzzle was, being able to form, the right partnerships, and being able to, find cities that are interested and also have the level of infrastructure that are able to provide the data that we need to have this situational awareness of what's happening on the corridor. So there was an awful lot of outreach that had to happen before we could settle on one corridor. And in fact, at first we thought it was going to be somewhere else. So that was a big part of the work at the very beginning. That's a great question.
Yeah, that's interesting. The other thing I just want to mention is, we're in South Carolina. We've had ramp metering in California since the 1980s. We still do not have ramp metering in South Carolina. So just wanted to mention that.
Okay, interesting.
So the students might not even know what ramp metering is one of the reasons.
Oh.
No, I think they'll know that. Yeah, because I teach that in my traffic class. So then I'll be in trouble if they don't know it. So yeah.
Yeah. What are ramp metering tickets now in California? And I'm really sorry for interrupting.
Oh, that's interesting. I don't happen to know that, and I haven't been caught for running one because I obey the rules.
That's awesome. Anyway, I'm really sorry I missed the presentation.
Okay, well, thank you so much for your questions.
So there's another question. Also, there was the answer over $200. The fine is over $200. Nick answered, so over $200. So there's another question. What are some of the future research questions that public agencies are interested to know from the I-210 ICM project?
Okay, so I'm not sure that I'm the best person to answer on behalf of these of public agencies. I think they're concerned about doing what's right for their city or for their jurisdiction. In terms of research, I think they're more interested in practically what's going to benefit their population. So it's hard for me to really answer that directly. What I am hoping is that if we can demonstrate success in connected corridors and demonstrate a benefit that cities and agencies will become more open to experimenting and using this kind of technologies and really buying into this idea of being collaborative and being cooperative and maybe even in the future really sort of connecting this up with say the Wazes and the Googles of the world, so that instead of having people just driving under the influence of apps, but that these apps are really working with cities and stakeholders to get to put the traffic where the cities want it, as opposed to letting it go wherever it goes. And so I think that's really what I'm hoping for, that there's more of this idea of collaboration and getting the private sector and the public sector working together to make things better for everyone.
Okay, thank you. So any more questions? So please ask. Now we have a few minutes, about 5 minutes, so we'll close down. So there's another question. So Dr. Patire, you mentioned that this pilot is planned to be deployed in May next year. Will it be jointly operated between the city and Caltrans traffic operations?
Yes, absolutely. So in the picture I showed, I had these different boxes, the green box, which was the Caltrans ATMS, and a purple box, which we call CMS, which is the another meaning of CMS. That's the corridor management system. So, and I apologize if I think it was Peggy who asked that question. So there are two interfaces. One interface that Caltrans uses, and there's another interface that we call CMS, which is that purple box for cities to use, right? And so it will be jointly operated. And the idea is that, from the very beginning, we wanted it to be collaborative, and any one jurisdiction that is participating in a response plan would be able to veto that plan. So, for example, let's say that there's something that the decision support system doesn't know about. What if there's a protest on some street and that wasn't in your lane closure system, right? Well, then the system doesn't know, but you would need in that sort of situation, an operator to say, oh wait, there's something going on this street that we better not send traffic there, right? So this will definitely be cooperative and by all the stakeholders. Thank you. Good question.
So Charlotte, do you see any more question?
No, I think they were all answered. I know Nick, you had a question, but I think it was covered by a previous question. Yeah, so we're all set here.
Yeah, my question was the size of the system. Is there a maximum size to the modeling that can take place, Anthony? I mean, reasonable. And how do you expand it? If do you expand it in that corridor, or if you expand it to another corridor that's nearby? How does that? I mean, does it just keep getting bigger and bigger, or do you have to parse it and separate it and somehow connect it in the middle with another one? That kind of thing. What's the next stage of largeness, if you will?
That's a really great question. Thank you so much. I think that the model that we have is really big, and I think if you're adding a parallel corridor or something like that, you really do want to break this up. I think there are a number of different ways, different approaches for that. I think that another really interesting thing is when you have multiple corridors interacting closely to each other, there are going to be new levels to systems of systems operating together. And it could be that if you have in an incident on one corridor, that might affect how you might want to manage a neighboring corridor. And those are really fascinating questions that we're working on right now.
Great, thanks.
Thank you, Nick. So it's 3, so just about time. So thank you, Dr. Patire. So it was a great presentation, as all the audience mentioned. So we learned a lot, and thank you very much for the presentation. So I will invite you back very soon. So thank you.
Thank you so much. It's been an honor and a pleasure, and thank you so much for all the great questions.